Hello everyone. So after learning about the duality in linear optimization, now we are going to discuss some of the characteristics of the dual problem and primal problem. So we basically want to see what was the goal of finding the dual. So let's say the original problem is minimizing C transpose X subject to AX greater than equal to B, X positive. So this is our primal. And then the dual problem is maximizing B transpose Y. B comes from here. Y, X subject to A transpose Y less than or equal to C. A transpose, C transpose transpose, which is C. And all of Y's are positive because we have an inequality constraint here. Alright, so the key idea is B transpose Y is always less than or equal to C transpose X. This is the key notion for primal and dual problems. This is going to hold even in nonlinear programming. So this is the value of objective function. Let's call this phi of x, phi of y, and let's call this f of x. So it tells me that phi of y is less than or equal to f of x at any certain point. What it translates in terms of the solution that we have is the dual problem provides a lower bound for objective function of primal problem. Okay, so the question that we can ask here, when this equality happens? Because if this equality happens, it means that you have achieved the minimum point that you can achieve in the primal problem. It translates into finding the minimum point or the optimal point of your optimization problem. So, let's keep this as it is. So if x and y are physical solutions for primal and dual problems, then C transpose X is greater than or equal to B transpose Y. And what do we call this? We call it weak duality lemma. Okay, let's keep this weak duality lemma in mind and see what we can conclude. So in the linear programming, as we said, dual and primal, they don't have any gap. So if you can find the optimal solution to the dual problem, it's going to be equal to the optimal solution in the primal problem. So the conclusion from this lemma is if x star and y star are physical solutions to primal and dual problems respectively, and. So there are two rules. First, X star and Y star are feasible solutions to primal and dual problems, and C transpose X star is equal to B transpose Y star. Then X star and Y star are optimal for their respective problems. Alright, what it tells me no matter what's your objective function, you can find a set of feasible solutions both for primal and dual. But exploring those set of feasible solutions, if at some point you happen to see these two values are equal, then you can guarantee that X star and Y star are not just feasible, but also the optimal solutions for the original problem. For the original problem and also for the dual problem. Now I'm going to talk about a sample of primal and dual problems. So we talked about the 7 or 8 rules to find dual problem in linear programming, but there are some simpler cases that you don't need to go over all of the rules. I'm going to share one of them here. So if the primal problem looks like minimizing f of x is equal to c1 transpose x1 plus c2 transpose x2. So x1 and x2 are set of variables, they are not only one variable. Let me remind here, x1 and x2 are vectors. So minimizing f of x, which is a function of x1 and x2, subject to the first set of constraints is a11 x1 plus a12 x2 greater than or equal to b sub 1. The second constraint a21 x1 plus a22 x2 is equal to b2. So one set of inequality constraints. So these are not only one constraint. A11 is a matrix. Set of equality constraints. X1s are all positive and X2s are unlimited. So using the rules, we can identify that, okay, for this one I need some limited variables in the dual problem. For this I need some unlimited variables in the dual problem. For this I need an inequality constraint in the dual problem, a set of inequality constraints in the dual problem, and for this unlimited variable I need some equality constraints. So here is how your dual problem looks like. It will be maximizing by is equal to b1 transpose y1 plus b2 transpose y2. Where does that come from? b1, b2 transpose gives us those coefficients. Let's see what happens to constraints. Variables are y's. So because we have x1 is greater than or equal to 0, so we will need inequality constraints here. And because x2 is unlimited, so we will need the second set of constraints as equality. Again, if you recall, we have C1 transpose, C2 transpose. We transpose them and bring them here as C1 and C2. We have a blocked matrix of coefficients for the constraint, A11, A12, A21, A22 transpose. So it will give me A11 transpose, A12 transpose, A21 transpose, and A22 transpose. These are the coefficients for this constraint. So I will have A11 transpose A1 plus A21 transpose Y2, A12 transpose Y1, and A22 transpose Y2. We have inequality constraint here, so we will need Y1, which is greater than or equal to 0. We have inequality constraints here, so it means Y2s are unlimited. This is one nice example of finding the duality, and it can be applied to several real-world problems. So I think that's all the details for linear programming. Yeah, we discussed all of the details from linear programming. So there will be only a few examples that I will solve in the next few videos, but now let's get into the nonlinear programming. Duality for nonlinear programming.